Algebra 2, Chapter 9, Section 5, Complex Numbers. Until today, we have been working only with numbers that came from the set of real numbers. And I've said before that we can abbreviate the set of real numbers using a blackboard R, which looks like this. This big bold side to the R. A real number is any number that's on a normal number line. So if you were to draw just a plain old number line, the numbers on that line would be the real numbers. Any number. So it could be a number like 0, or 1, or 2, or 3. It could be a real number, could be negative, -1, -2, -3. So these counting numbers are the first numbers we learned, 1 through 9. But then we start to learn bigger numbers as we progress in our math knowledge. We learn about 0. Then we learn about fractions. So we might have a half, 1/2. You might have 5 halves, or even complex fractions like 2.5. They're the same number. You also could have negative numbers. We learn about those to the left of the number line. So we have this long line of numbers. Then we learn about numbers that are not rational, can't make as a ratio between other numbers, like the square root of 2, which is about 1.414, so it fits in the line here. Or we learn about other kinds of numbers that are even not from square roots, like pi, which was about 3.14. All these are on our number line, and they're all real numbers. The solution to the equation x squared equals -1 is not a real number. It does not, that number does not fit anywhere on this number line. However, we can define a new kind of number called an imaginary number that is the solution to this equation. Okay? So because we want to be able to solve these equations, they may have useful solutions for certain applications of quadratic equations. So to solve these, we invent a new kind of number. Invent is the wrong word. I guess we've discovered a new kind of number, and we call them imaginary numbers. We define the basis of this imaginary number system as a letter I, and we define it to be the square root of -1. And I we call the basis of the imaginary numbers. And I is very much like 1, which is the basis of the real numbers. If we multiply anything by 1, we get 1. If we multiply anything by, if we multiply any imaginary number by I, though, we don't get I. We'll see that later. But anyway, it's the basis. It's the building block. We can add to it. So we could have 2I and 3I and -2I. Okay, so we could have a new number line that we invent, or not invent, we discover, I guess, that we could do this. That's perpendicular to our old number line. So if these are the real numbers, we can have an imaginary number line. And in our imaginary numbers, 0 is the same thing. So 0 is both an imaginary and a real number. It's the only number that's both. Okay? That's where they intersect. And we have I. We have 2I, we can have -I, and we can have -2I. This should remind you of the Cartesian grid that we graph functions on. Okay, so the imaginary numbers are the numbers on this line, the imaginary number line. Okay, and at this point it's good to talk about this. Imaginary numbers are not less real than real numbers. Okay, a real number is actually an abstract idea that's useful in analyzing things that we observe in the world. So are imaginary numbers. They're a useful idea for analyzing things we also find in the world. Okay, so we might use positive numbers to indicate going forward on a line in a problem, and we could use negative numbers to indicate moving backward. Now we could use an imaginary number for moving left and right. So there's lots of ways we could apply this idea outside of simply pure mathematics or algebra. Now we're going to mainly study just algebra for imaginary numbers and complex numbers, but don't forget that they have real applications. Don't think that they're more imaginary than real numbers. I think the genesis of this name imaginary is because it requires using your imagination in order to apply them. Okay, you have to be creative. Maybe a better word for them would be the creative numbers. Okay, instead of the imaginary numbers. And next we'll talk about complex numbers. So a complex number is simply a number that is the sum of a real number and an imaginary number. And a complex number has a standard form. A is the real part, which you can abbreviate RE if you need to abbreviate it, and BI is the imaginary part. Okay, so this is a real number, A is a real number, and BI is a complex number. B is the coefficient of I, and I is the square root of negative 1, as we defined previously. Z is the name of the whole complex number. So a complex number, unlike any other number we've studied so far, has two parts. Okay, this number has two parts, which means if you wanted to graph the number, we can't graph it on a line. If we wanted to graph the number, we would have to graph it on a grid. Okay, so if we have a real axis and we have an imaginary axis. And if A were 1, the real part were 1, and B were 1, and the real part was I, our number would actually be here on this grid. Instead of being on a line, complex numbers are on a grid. So that's a little bit complex, which is why we call them complex numbers. They have two parts. Okay, so adding and subtracting a complex number is straightforward. You just add the real parts and the imaginary parts. Multiplying complex numbers, you use the distributive law, and we'll practice this in a minute, and you'll see the result that you get is still a complex number. Dividing complex numbers is more complicated. First, you multiply by a fraction, which has a numerator and denominator set to the complex conjugate. So if you have Z1 divided by Z2, we're going to multiply by the conjugate, which I'm just going to put a bar over it to mean conjugate, of the denominator divided by itself. Now this divided by itself is still 1, even in complex numbers. And so we can multiply by 1 and keep this the same value. And so now the only caveat being this Z2 can't be 0, which it couldn't have been 0 here anyway, because you'd have an undefined thing. So we have the result of this, you actually get a complex number that has no division, and you'll see how that works. It's similar, this is similar to, very similar to rationalizing a fraction, denominator. Rationalizing the denominator, we'll just call it the denominator, because that's really what we're doing. We're getting the square root of negative 1, the imaginary part, out of the denominator. Okay. And we'll also talk about what happens if you divide a complex number by just a real number. So if you have a complex number and you divide by some other number, it follows the same rule of fractions we've already learned. So you would have a over 3 plus b over 3i would be the answer. Okay, so the only trouble you have is when you're dividing a complex number by a complex number. Okay, so we're going to practice some complex arithmetic using the rules we just learned. And these rules all come from the definition of I, okay? Every one of them comes from the fact that we've defined I to be the square root of negative 1. Okay, so let's start with A. We have an addition problem. Okay, so we could drop the parentheses just like we could with any addition before. And we have 2 plus 3. Those things don't have I's. Not that they're blind. Ha ha ha. But that they don't have the letter I next to them. And then we have 7 plus negative 5, which is the 7 minus 5, or 2i. That's the answer. B. So addition is straightforward. B, we have a subtraction. All we have to do is distribute the negative. So we have these two complex numbers being subtracted from one another. Distributing the negative, we get 5 minus 4i minus 8 plus 3i. And that equals 5 minus 8 is negative 3. And negative 4 plus 3 is negative 1. We can drop the 1, just write negative I. minus 3 minus I. C, now we have a multiplication. We have to do our distribution. So multiply 4 by 5, we get 20. Multiply, so it's the first, the outer, 4 by 2I, and we get 8I. The inner is 6I times 5, which is 30I. And the outer, we get 6I times 2I, which is 12I squared. Okay, now you might think, oh, we have this I squared, but think about this from the definition. If we square both sides of this definition, we have I squared equals negative 1, which makes sense because we defined I from the solution to this equation. So squaring I just gives us a real number of negative 1. So this I squared is negative 1, so we can rewrite this, and we can combine 8 and 30 to 38I as plus 12 times negative 1, which is negative 12. 20 minus 12 is 8. So we have an answer of 8 plus 38I. This is another complex number. It has a real part and an imaginary part, and it's in standard form. Be sure you put all your answers in standard form for complex numbers. Also, I forgot to mention this caveat. If you have a plus or minus here, that's okay for standard form. So if when you did all the math, you got two answers that were a plus and minus, you can write your complex number like this. That still counts as standard form. Okay, so D, let's put D here. So D, we have another multiplication, and then we have an addition as well. So 2 times 4 is 8. 4I times 4 is 16I. Minus I times 2 is minus 2I. And 4I times minus I is minus 4I squared. Okay. So 8 plus 16 minus 2 is 14I. And then I squared was negative 1. Negative 1 times negative 4 is positive 4. 8 plus 4 is 12. So the answer is 12 plus 14I. And that brings us to E, which is the most complicated one, division. So now we need to divide these two complex numbers. So remember, the solution is to do what we do with rationalizing the denominator, multiply by the complex conjugate, or just really, you can think of it as the conjugate of the complex number. We just call that the complex conjugate for convenience. And make sure that you multiply by something that's 1, so the numerator and the denominator has to be the same. Okay, that gives us a multiplication to do in the numerator and a multiplication to do in the denominator. Okay, so the multiplication in the numerator gives us 2 times 3 is 6. 3I times 3 is 9I. Minus 2I times 2 is minus 4I. And 3I times negative 2I is negative 6I squared. In the numerator, we get 3 times 3 is 9. And like any conjugate, the outer and the inner are going to subtract away. So you'll have minus 6i plus 6i. So we don't have to write that down. It's the whole reason we had a conjugate here, okay? But plus 2i times minus 2i is going to give us minus 2i squared. Okay, so now in the numerator we have 6. 9 minus 4 is 5. And then we have minus 6 times I squared. I squared is negative 1. Negative 1 times negative 6 is positive 6. Now in the numerator, sorry, that is the numerator. In the denominator, we have an I squared, so that's negative 1. So we get plus 2. Okay. So 6 plus 6 is 12. Divided by 9 plus 2 is 11. And so that gives us 12 11ths plus 5 11ths I. Now why did I break the fraction up? Because we need it in standard form, and the standard form was real part plus imaginary part. Okay, so you can't have, this is not standard form, but this is. Be sure you always put your answers in standard form. So the whole point of multiplying by the conjugate of divided by itself is to get the denominator, the thing on the bottom is the denominator, to get the denominator to be a real number. when you multiply a complex number by its conjugate, you're going to get a real number because the first is a real number, the outer and inner go away, and the last becomes a real number because you have an I squared, which is a real number. Okay, and so that will give us a real number in the denominator every time. Okay, so hopefully you all are paying attention and caught all my mistakes in this work. If you weren't, then you need to pay closer attention and you should be noticing the things I got wrong. Okay, so let's go back now and look at what I've done wrong. So we have in part A a mistake. We have a problem with this sign because we have A 7i minus 5 should be positive. So if you work too fast, it's easy to make a mistake. Don't do that. Don't work too fast. Then in part D, forgot completely about the second half of the problem. So this is not the final answer. It always helps to go back and look at the work and see if you've gotten your every part of the problem written down. Okay, so we forgot to add the second complex number, 6 plus 10i. So we need to add the real parts, 18, add the imaginary parts, 24i. That's the right answer. And then hopefully you caught the error here in E as well as you were watching, and that this is not supposed to be a 2. We have 2i times negative 2i. This has to be a 4i squared. These should always be perfect squares. That's another thing you can catch, because we'll always have a 3 times a 3 or a 6 times a 6 or something that'll be a perfect square in each of these two entries since we multiplied by a conjugate. And so we have 2 times 2 should be 4. The denominator here should be 13, not 11, because 9 plus 4 is 13. And now we have the right answer. So pay attention, and if you catch me making a mistake, let me know. Now, hopefully you noticed as we were going that we applied this idea a lot, that I squared is negative 1. Okay, because I times I, I'll write that here, I times I was the square root of negative 1 squared, which is negative 1. Okay. Now we can think about some other powers of I. If we think about I to the 0, that's just like any other number to the 0 should be 1. That was a rule we learned of exponents. I to the first power, anything to the first power should be itself. So that would be I. I cubed would be I times I squared. And remember, I squared is negative 1, so we get negative I. I to the fourth would be I cubed, which is negative I times I. Okay? Maybe I shouldn't skip a step. I times I cubed, so that's I times negative I, which would be the same as negative I squared by rearranging the negative 1 and the i's. And I squared is just negative 1, so you have negative 1 is 1. I to the fifth is I because we multiply 1 by I. I to the sixth is negative 1 because I times I is negative 1. I to the seventh is negative 1 times I, negative I. I to the eighth is negative I times I, which is like I to the fourth is just 1. So we have this pattern that repeats forever. The powers of I go through this sort of cyclical pattern. Okay, and you could think of it almost like a wheel with 4 spokes. If we have this as the real and imaginary part, and this is 1, this is I, this is negative 1, and this is negative I, then I to the 0 is 1, I to the first is I squared is negative 1, I cubed, let's draw that again, I cubed, let's move this to be a little bit more like where it would be, minus I cubed would be negative I cubed to the fourth, let's see, I to the fourth, which is multiplying by again is 1, multiply by I again, we get I, multiply by I again, we get negative 1, multiply again, we get negative I, multiply again, we get 1. And we go in this circle over and over and over again. And if you can also go backwards in the circle if you divide by I. Think about going on negative powers. And this pattern repeats continuously either direction forever. So we can use that to write in general when I to the n equals I when n is 1, 5, 9, 13, and so on. I to the n is negative 1 when it's 2, 6, 10, 14, and so on. I to the n is negative I when n is 3, 7, 11, 15, and so on. And I to the n is 1 when n is 4, 0. We saw 0, 4, 8, 12, 16, and so on. And the negative powers also work here if you are curious about that. Negative 2, negative 6. They all follow the same pattern, both forwards and backwards. So let's talk a little bit more about this idea of the complex numbers being on a grid. So if we draw two axes where the horizontal axis represents the real numbers, the real number line. This is the real number line. And the vertical axis represents the imaginary number line. Okay, so if we make 4 units 1 for the sake of our scale, then we can write some scale information on the number line here to give us an idea of where our numbers are. So this would be 2i all the way up here at 8 blue lines. Negative 2i on our graph paper. Sorry, negative I. Hopefully you caught that mistake when I made it. So I'm just trying to see if you're awake today and paying attention. Minus 2i. Okay, so here's our grid or our plane. Okay, we could call this the complex plane because it makes a plane in a geometric plane, an infinite sheet that goes every direction. Instead of a line, which is what the real numbers made, was a line. The imaginary numbers made a line. The complex numbers make a plane. So if we were to put 3 plus 2i, if we were to graph that number on our plane, then we would come to 3 as the real part, 2 as the imaginary part. The number 3 plus 2i is right here on our complex plane. If I say, where's the number 5 halves? Well, 5 halves has no imaginary parts, so it'll be on the real number line at 2.5. So here's 5 halves. What about the number I? The imaginary number I is right here on the imaginary number line, already labeled I. What about 3 halves I? 3 halves I would be 1.5 right here on this imaginary number, on the imaginary number line. What about the number negative 3 halves plus or minus I over 2, or we might write that even as 1/2 I to make it really plain. So 3 halves, negative 3 halves in the real axis is here. This is actually two complex numbers. There's the positive version at 1/2 I and the negative version at negative 1/2 I. Okay, so this is minus 3 halves plus I over 2, or 1/2 I, and this is minus 3 halves minus 1/2 I. Right, this is plus 1/2 I. So you can see those two numbers are complex conjugate pair. We have the number in its conjugate, which happens a lot when we're solving a quadratic equation. So from now on, we might be able to solve a quadratic equation and write the answer as a complex number. So let's do that real quick. We could even graph the number if we wanted to. So let's make this not a graph page, but make it a plain page of paper. Let's give it lines actually. Okay. So this could be our homework. Put our name on it, the date, and then put, let's just work a problem here. Let's try one of our homework problems. Let's solve the equation that's number 28 in homework. X squared minus 12x plus 45 is 0. So if you're told to solve this, this doesn't look like something that's easy to factor. And in fact, if the answer is a complex number, we won't be able to factor it with real numbers. So let's just put this straight into the quadratic formula. So we have x is minus b, which was, so minus b plus or minus the square root of b squared minus 4ac. Hopefully you've memorized this by now, over 2a. So minus b would be 12. B squared is 144. Minus 4. A is 1 and c is 45. Over 2a. A is just 2. Okay, so let's pull up a calculator. And we will find what 4 times 45 is 180. And 144 minus 180 is negative 36. 12 plus or minus the square root of negative 36 over 2. Okay, so before we would have written no such answer, or no real answer. But now we know how we can write this as a complex number in standard form. So we can go ahead and split our fraction up. So 12 divided by 2 is 6, plus or minus, and the square root of negative 36 would be I, which is the negative 1 part, times the square root of 36. And 36 is a perfect square, so we can write this as 6i divided by the 2, because 6 times 6 is 36, and I is the square root of negative 1, and 6 divided by 2 is 3, so we can write the answer 6 plus or minus 3i. And we could graph this on a complex number plane. It won't fit on the one that we just drew on the previous page because the scale is off. But if we could just draw the plane out like this and write our real and imaginary axes, and we could have 6 as the real part and plus 3i is one imaginary number and minus 3i is the other imaginary part. So the complex numbers are here on our complex plane. So this is a little bit of a different idea, that a number can have two parts and that the number itself doesn't fit on a line, it fits on a plane. And that idea came from the fact that we have a real number line crossing an imaginary number line that's perpendicular to it, which defines this perpendicular axis system we can draw or graph the complex numbers on.